Good morning, class! Hello, 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 hello. Testing. This is my test, audio test, etc., etc. Boop. There we go. Cool. Alright. Hi. How's everybody doing today? I hope y'all doing well. It's a wonderful day in November here in my own personal little Corona bunker. And we're going to learn about classes in Python today. It's going to be just an epic journey of knowledge and inspiration. I hope y'all ready for it today. Because I don't know if I'm ready for it today. How is everybody doing today? I hope you're doing well. Download already! My goodness. It's almost like I should have done this beforehand. It's almost like he says that every time. Shush, inner voice. Alright. So. Yeah, this is about where we were. Cool. So, we're still in classes land, and we've got a reasonable amount of material to get through, so let's not delay and get right to it. Last time, we were talking about how one might go about invoking methods that have been defined in a class. Oh, I should actually have my lighting set up properly. How do I look? That's better. Good. We were talking about how you would go about overloading classes, or overloading methods that are provided by the default class in Python, one of which is init. You'll know that you're overloading a method that's provided by default because you have your method name with 2 underscores on either side. That's Python's designation for it. So we had just seen how you might go about overloading the equality operator as well as the initialization operator. And we had just gotten into the idea of inheritance. So inheritance is a bit of a tricky concept, but the general idea is that when you define a class, you can make another class which has everything in that class by having the new class inherit the old one. We also sometimes say that the new class extends the old one. So this is our example with colored point. You can see that in addition to x and y, we have this new parameter color, which of course has corresponding argument provided in init, so that now our object of class colored point has 3 attributes instead of just the 2. The color is new. And we provide a method darken, which allows us to modify the color by making it darker, in the same way that, we had the make old function for person. The thing that is interesting about this is that implicitly, because we have imported point, we also still have all of the methods defined in point available to the class colored point. So if we want to invoke, for example, distance or a scale, we don't have to do anything else. Those are still defined for colored point because colored point inherits from point. So that is how that works. Any questions about that so far? Am I breaking? Am I breaking up? No, that's okay. I'm just enthusiastic today because I actually got a reasonable night's sleep last night for the first time in like a week. So, yes. So, in addition to overloading equality, we can now So equality was already overloaded for point, right? So rather than redefine that that functionality that was encapsulated in the old redefinition of equality, we can make reference to the methods that are contained inside of the class we are inheriting from by using dot notation and reference to the class name. So we can return point.eq. This invokes eq as it was defined in the point class. So this line of code right here gets substituted in where your, you know, essentially where your where that invocation occurs in the colored point class. And notice we are performing Boolean AND operation with self.color is equal to other.color. So we are taking the equality comparison for the point class and adding to it the condition that you must also have the same color in order for the point to be considered the same point. So you can see this demonstrated down here. Colored point, which is yellow, and Q is a colored point, which is pink. And is P equal to Q? I think not. However, it would be nice to have that actually demonstrated, wouldn't it? Let's just throw this stuff in here, and hopefully things work out. Copy that. And of course the indentation never works out, but you know, whatever. Whatevs. We'll just fix it. Oop. Of course, if we want colored point to inherit from point, we should actually include the point class in here as well, shouldn't we? There we go. Normally, it's nice to put a space between your methods. Generally speaking, the slides don't do that because of space consideration, but, you know, if you have a whole file, you can space things out a little more nicely. So, if we have... there we go. Copy that. There we go. Python 3. What do we call this silly thing? Classes dot py. There we go. Oh, we've got a syntax error. Indentation error. Expected an indentation block. Ah, that would do it. That would do it right there. If you're going to do an empty class, you have to at least put a pass in there. Otherwise, the Python interpreter has nothing to chew on. String is not defined. Yeah, okay, we'll just get rid of that entirely then. Can I make this bigger? Let's see if I can make it bigger. Preferences. text. Custom font. There we go. We'll blow that up to maybe a 24. Maybe a 20. 20 will be probably plenty. Select! There we go. There we go. A little bit more readable for you folks. So, if we call classes.python, boink, there we go, we get false. False is corresponding to this equality comparison right here. Boop. So, here's a question. Why isn't this doing anything? Print P. See what you say to that. Main colored point object at that thing, color equals yellow. Ah, I see, okay. Was that in the... No, that wasn't in the previous. That's interesting. All right, so we're overloading... what I haven't done here is I haven't redefined point.string in order to, make it other than the default. So let's add that quickly. Def string self is return self.x string convert self.x plus comma concatenate string convert self.y concatenate the end of that, and I think that we will just have it go like this for no particular reason, because it looks pretty. There we go. All right. If we... I'll just close that window. Yes, there we go. If we run this again, you can see that the first thing that it does is it goes into the method that we defined in the point class that converts to a string, and then it, computes the rest of the expression, which is this the square-braced thing where we insert self.color. Technically speaking, I don't think we need to string convert self.color since it's already a string. However, if it was not a string, we would need to string convert it because, Python being Python does not strictly, it does not strictly restrict the typing of things. So, man, sleeping is the best thing ever, I have to say. What is the significance of so that character is an artifact of the encoding in the slides. It's not a legal operation in Python. This is simply meant to indicate that the expression is continued on the next line. And that is in the slides. That's why you saw me delete them out of the code when I actually tried to, put it there. Otherwise, the font would have to be super, super, super tiny. So there we go. So that's some messing around with classes. Hopefully, you guys. Are there any questions about method overriding? Are there any questions about the stuff we've talked about so far? Questions? Okay. I'm going to assume that you guys are okay. So, One of your esteemed colleagues last time asked what is essentially the purpose of this system of this inheritance idea. How is this idea of inheritance applicable to my life as a human being? Well, so it's interesting because it works on the analogy of a class to a physical object. So, or, you know, things that actually exist. It's a so whereas in physical existence, for you, a physically existent human being, when we think about certain things, we tend to think of them in categories, right? We tend to categorize things, we classify things. If you think about it, the human brain is actually one gigantic classification engine. If you think about this, this is a book. Books have known properties. There are things that are particular about books that are unique to this particular object, which is an instance of the book class, but in general, the books can be relied upon to share a certain set of properties. In particular, they are typically made of paper and have a bunch of pages on which information has been written, although the nature of the information written on the book can vary widely from book to book, as can the particular way in which a book has been constructed. Although books are of a large number of general constructions, one can reliably expect a book to be a bunch of pages that have been connected together in some manner that makes it, depending on what culture you're from, they can be from the back or from the front. The concepts of front and back are relative to the cultural context, of course, but generally speaking, a book is an instance of the this object is an instance of the class of books. That's a way of thinking about it that's in line with how we do classes in an object-oriented sense. So the thing about it is that there are subcategories and sub-classifications within a particular classification. So going back to this book analogy, although it is a book and it does everything a book can do, it is also a textbook. So it does everything that a textbook could be expected to do. For example, it is a generally accepted phenomenon that textbooks, at least textbooks in the undergraduate sense, have exercises in them which you can use to practice material that is presented in chapters, and also the organization of the book is roughly into chapters which each deal with a different aspect of programming in a particular language. In fact, the fact that this is a textbook on programming on a particular programming language puts it in the class of programming textbooks. We can continuously narrow down the classification of things until we have arrived at a very specific class of objects. So, but the point is, a programming textbook inherits all of the properties of a textbook, and a textbook inherits all of the properties of a book. Right? All of the properties and methods, actions which you can orient to them. So, this analogy goes so far, so good into the realm of, it's fine insofar as we're talking about properties. We may wish to extend this analogy to actions. So, if you think about a book and your mechanisms of interaction with a book, generally speaking, there are a number of things that you can do with a book. You can open a book to a page. So, def open, self int I, although you don't get to declare it as an int, where I is the page number. That is an action you can perform over a book, and that action would be inherited all the way down through the all of the that would be native to the book class and inherited by textbook and programming textbook. However, you would have something like, say, lookup ASCII table, right? Lookup ASCII table. Generally speaking, most programming textbooks can probably be relied upon to have an ASCII chart in them somewhere at some point. So, looking up the ASCII table in a programming textbook would be a method of a programming textbook that would not be shared by textbooks generally or books generally. It depends on the particular construction of a programming textbook. So you can think of it in that manner, and you can also extend this idea to animals or people. So generally speaking, in terms of people, most people can be relied upon to perform certain actions based on the fact that they are human beings. Like, for example, most people breathe. And so, there are certain exceptions, of course, as there are to any system of classification. The trick is to not understand classification systems as things that have to be rigidly adhered to in physical reality, although they are things that are rigidly adhered to in cyber reality. Generally speaking, human beings breathe and their heart beats, and they can be relied upon to digest food. Once you start going down the hierarchy of types of human beings, we can have, children, adults, and the elderly. That would be one system of classification. Children share some common attributes, the elderly share some common attributes, and adults share some common attributes. Of adults, you could, for example, break them down by profession. So you might have, maintenance workers and artists and dentists as being types of humans. You could even break the professions down by classification. And the whole idea is that at each level you're breaking things down, you're introducing attributes and actions which are common to both that class and all the subclasses which inherit from that class. So, if you consider surgeon to be a class, then you might have heart surgeon, brain surgeon, and oral surgeon. Each one of these guys can be relied upon to know how to use a scalpel. However, each one of those will have very specific knowledge about their particular area of surgery that's not shared by the surgeon class. Well, anyway, I might be belaboring the point, but the idea is that when you are constructing classes in a programmatic sense, you are constructing models of the manner in which things are classified in reality. So that's sort of one way to think about it. Let me see if I haven't completely confused people in the chat. So the default setting of the book class is paper. I would say that there would be a few other things other than it just being paper. It needs to be paper that has been bound together, and it probably should have page numbers. But aside from that, yes. Class textbook extends book for int I equals 0, I is less than book.end, I++ absorb book. Yes. So comp sci textbook inherits everything from book unless it was overridden by textbook. Yes. Good. Yeah, so there you go. That is like a mental model for how do you work with classes. So, going back to our colored point example, we have object, which is the most general thing. We've got point, which inherits from object, and we've got colored point, which inherits from point. Type X will tell you the type of the object X. So, if we, for example, the type of P in our colored@point example will be main.coloredPoint. If we instantiate a regular point, let's say r is equal to point 7 of 9, Star Trek reference, then, and we, if we try to print what the type is of that one, we get main.point. So this is fine. This is good. This is, we can tell what an object, what class an object is in using type, but how do we tell if something inherits from something else using a function? We use isInstance. So if we change type to isInstance here, isInstance, there we go. We can check to see if a particular object is of a particular class, or is an instance of a particular class, or inherits from that class, is or inherits from. So, for example, is R an instance of point? Yes, R is an instance of point. Is R an instance of colored point? No, it is not. That turns up false. So, and because, you know, R is a point, it does not, it's a more general thing than a colored point. It's not a colored point. It doesn't have access to the things that colored point has access to. That's how these classes work. Colored point has access up the tree, but things that are higher up the tree don't have access down the tree. So object does not access point, point does not access colored point, but colored point accesses both of the things above it. Cool. Okay, can someone help with the self thing? Okay, I'm glad you asked that question. So, the way that methods work in Python is that the first argument is always, it references the object upon which the method is called. So, for example, in our colored point example, if we take P and we darken it, we call the darken method on it, there are two ways that we can do that. We can either go p.darken. That means that this guy is implicitly self. This is exactly equivalent to point.darken p. In this construction, the argument lines up explicitly with the self argument. If you tried to do this, you would get an error. It would say that there are too few arguments for this particular invocation. Attribute error, type object point has no attribute. Oh, yeah, well, I also have to do that on a colored point, wouldn't I? Yeah, darken missing one required positional argument self. So basically, in order to call a method, that needs to be linked to an object of the type, an object of the class that the method is contained in. You know. So, inside here, self is the object on which the method is being called. So when we say self.x or self.y, we are designating those as attributes of the object which is being initialized in this case, because we're doing the init method. I don't know. Maybe that helps. Yeah. Scott's explanation is okay. Yeah. So let's talk about multiple inheritance. So we've talked about inheritance, but we also have an idea of multiple inheritance. So it is the case that a class does not necessarily need to inherit from only one other class. A class can inherit from multiple classes. So if, for example, we wanted to abstract out the attribute color, because maybe we want, colored points, colored lines, colored figures, maybe we want to apply the attribute color in a way that means we have a filled figure, there are many ways in which we could apply an attribute color. And, if you think of color as being a slightly more complicated thing than the way that we're currently representing it here, like if you consider color as being RGB or HSV values, like a set of HSV values plus an alpha, as is the case when you are, doing things in Photoshop or, similar image creation, or, applications which care about color. That's a way that color is often represented. You can imagine color as being a class, and anything that needs a color attribute can inherit from that class. There is some use in abstracting it. That way, if you need to make some modification to the code that controls color, you only need to make that modification in one place, inside of the color class. So, if we wish to construct a colored point class using a point class and a color class, we might define our color class separately, like so. We have an initializer, we have darken, we have EQ, and we have string. And in order to construct our class which inherits both from point and color, you can see that we are invoking both the initializers for point and color, the equivalence comparison for both point and color, and the string conversion for both point and color. This way, color can be inherited in other classes as well. Reusing code through inheritance contributed to the popularity of object-oriented languages. It is a powerful mechanism of abstraction. So let's talk about abstract classes. This is not necessarily, you'll see, it's a little bit of a academic point, but, So an abstract class, there's nothing specifically that designates a class as being an abstract class. It's the way that you use it. So if you have a class which only serves as a basis for inheritance, so you would never, for the example of color, you would never have just a color. The idea of color being a thing that exists unto itself doesn't really make sense, even in a physical sense. You don't talk about, man, I got a delivery of red by mail last week, or what I really dislike is all of this orange on my front lawn. You wouldn't say that. You would say, I dislike all of these orange leaves on my front lawn. Like color is an adjective. It is only really meaningful when it's applied to a noun. So, when you have a class that functions more like an adjective than a noun, that is called an abstract class. It's never really meant for object instantiation. It's only meant for inheritance by other classes. So, the purpose of this, of course, is code reuse. But yeah, it's kind of an academic distinction. There's nothing syntactically in the code itself which designates a class as being abstract. So, let's talk examples. Let's do a birthday calendar. Our task, should we choose to accept it, is to design a birthday calendar with the following operations. Clear, which removes all names from the calendar. Add, which adds a name with a date to the calendar. Contains checks if a name is in the calendar, and birthdays on date, the set of names with birthdays on a specific date. This requires a data structure with entries for names and dates. The data structure is shared among the operations. A class allows to produce an implementation. Let's make a new file. Doop-a-doop. Get it? bday.py. There we go. So, class bday inherits from object, because why not? So we have to choose the mechanism that we're going to use to store our data. Since we are relating dates to names, both dates and names are non-numeric, and like this is a mapping between two things. So I would suggest that what we're looking for is a dictionary here. But we kind of have a choice to make. We can either provide, like, we can either do names as the keys and dates as the values, or dates as the values and names as the keys. Since implement R, I would argue that it might be easier, it would make the birthdays method easier to implement and wouldn't make the other ones all that much harder if we had the dictionary built up such that we related dates to a list of names. The list of names being the people who have a birthday on that birth date. It's almost like a hash table in that sense. So let's go with that. Self.bdays is equal to an empty dictionary. Def, so what do we need? What are our operations here? We need clear, self, we need add, self, name, and date. We need def contains, self, and name. And we need birthdays, self, and date. So, clear is easy. Clear is just, in order to delete everything in the dictionary, you just reinstantiate it as being an empty dictionary. Done. You could even, if you want, do that. You could do clear self. I might have to do bday.clearSelf. I think clear self should work. Let's leave it. So, cool. If we wish to add, let's do add next. So if we wish to add a name and date to the birthdays, the first thing that we need to do is we need to establish whether or not the date that we want is already in the dictionary. So, if date is in the self.bdays, because remember, that searches the keys by default, not the values, then what we do is we say self.bdays at date is equal to this guy plus name. So we are taking self.bdays at date, which is a list. It'll be a list of names, and we are just concatenating the new name onto the end of the list of names. Easy peasy. However, if the date does not exist in the dictionary, we wish to add it to the dictionary. So, self.bdays date is equal to name. Obviously, it can't concatenate to itself because the value for this particular key has not been instantiated yet. That is the purpose of this assignment statement. It instantiates the new date value. Cool. Oh. Am I lagging? What if you do both, make two dictionaries? That would be a waste of memory, sir, in my opinion. Are we doing okay? Cool. All right, all right. So, going back to our birthday calendar. So, to tell if the dictionary contains a particular name, we need to search the values rather than the keys. So, unfortunately, this is the operation that was made more complicated by the fact that we made the dates the keys and not the names the keys. However, it's still not that bad. All we have to do is for entry in self.bdays if name in entry dot value? Yeah, how does it work again? I think that gives you the key. So self.bdays at let's call this key then. For every key in self.bdays, name in self.bday at key. If it is there, then return true. True. And if you get through all of that without having returned true, then we failed the search operation and we return false. There you go. And of course, if we wish for all of the names on a particular date that's in the dictionary, then we just simply return self.bdays at date, and that is all you need to do. So there you go. So there we go. So let's see how we did in comparison to the version in the slides. Birthday calendar. A birthday calendar keeps track of person names and their birthdays and allows to query who has birthday on a given date. So self.calendar is empty. That's good. This is how we did. Yes. Clear. Same thing. There we go. Add. Adds name with date into the calendar. Ah, see? So they have oriented the calendar towards names. So we'll get to see both versions. There you go. So, calendar at name is equal to date. Contains. So, the assumption that's being made here is that a name will not be duplicated. Personally, I don't think that's a good assumption. I think that it's entirely possible to get, like, 3 people named Mike in the dictionary who all have different birthdays. You know, it's improbable that a person has, like, your first name, your middle names, and your last name, sure, but, you know. I would say that names... the implicit assumption is that names should not be duplicated, but the implicit assumption is that birthdays, it should be possible for multiple people to have the same birthday, whereas it's not, you know, the converse isn't necessarily true. So, contains, that's the one that's being made simple in this version. So, return name in self.calendar. If name is in the keys, then there you go. Perfect. and birthdays, this is the one that's made more complicated. Notice they do something very similar. They create n, which is an empty set, for entry in self.cal. If self.cal at e is equal to date, n.add e then returns n. So it traces through each of the entries to check to see if the date that's associated with the name is the date you're looking for, and then it builds up a data structure that contains all of the names that it's found on the fly and then returns that data structure, which is fine. And then there's a string conversion function that wasn't even asked for. So there you go. Any questions about that? My camera is lagging. Is the audio lagging, though? I think your method, which is using dates for keys, is more sensible because when you look at a calendar, you mostly check the dates. Right? Right? Okay. Okay. Just for my own peace of mind, I'm going to do an audio. I'm just going to do an audio sync check. Yeah, I can see what you mean. Okay. All right, well, I guess we'll just keep going then. Don't have much time in class anyway. So, let's see if we can round out mean calculator. So, mean calculator, our task is to design a calculator for arithmetic mean with the following two operations. Add n, which adds n to the collection, and mean, which returns the mean of the collection. The mean should account for the same number being added multiple times. So, we've got, we're actually in the slides going to do several implementations of this, so let's call it mcalc1. Inherits from object, because why not? Define init. Oh wow, I misspelled this up here. That's what I get for not compiling. Init. Self. We'll keep a record. So we'll do self dot record is equal to an empty list. Def add self and n. Self dot rec is equal to self dot record plus whatever n is. We concatenate n to the list. And def mean takes self, because they always do, so, is returning the sum of self dot rec divided by the length of self dot rec. There we go. So, there you go. Very, that's exactly how you would do it. So, very quickly, the advantage of this is that you are actually keeping a record of all of the data points that have been entered. So, if you wish to expand this class in the future, in order to, compute more complicated things over this data set, like, for example, standard deviation, where you actually do need to know what all the numbers are, then, that this class would be amenable to that type of expansion. However, the disadvantage is that you are saving in memory each individual data point that has been given to this class. It's not actually necessary to save every single individual data point in order to calculate the mean. You can, in fact, just keep a running total of both the sum and the number of elements that have been fed in so far, and that will also calculate a mean for you. And that's what we're going to see next time in class. Thank you very much for your time and attention. would I need a try except? I'm not sure why you would need a try and except in this particular instance. But yeah, anyway, I'll stick around for like a minute or two to take questions. But other than that, I've got another class to get to. So, if you guys have a question, please ask it quickly. Also, like and subscribe. Ho ho. So, to the question, what if the length is equal to 0? What if nothing has been added? What's the mean? Yes. Yeah, that would be, yup. Good catch. So, try. Return that. Except. Return 0. Nice catch. That's a good catch. Because the problem is, if you haven't added any elements to the mean calculator, then the length of the list is going to be 0. And if the length of the list is 0, then you will trip a division by 0 error, which means that, you know, that's problematic. So you either want to try, you want to catch that with error handling, or you might even just want to let that pass on through. So there you go. Cool. Does every class declaration need an init method? Yes. Yes, it does. Can you do self.bdays.values? Yeah, I think, yeah, maybe you could, actually. Well, except the self.bdays.values would get you a set of lists, right? So even if you got those, you would still have to search those individual lists for, like, it's if you did self.bdays.values.concat, then you would get one list that contains all of everything over which the in operator would work, but you would need to concatenate all of those lists together. But yeah, anyway, thank you very much, folks. I'll see you guys on Thursday. Oh, yeah.